This is part 2 of a series on convex optimization. In this video, we will look at EQP, IQP, and Lagrange methods. This video was produced in Korean and translated into English. My voice was generated using AI, text-to-speech. In this video, we will look at how to solve constrained EQP and IQP problems using the Lagrange method. We'll also look at how to use slack variables. The first type is an EQP problem with equality constraints. Let's look at the optimization problem below. The problem is to find the minimum value of this function. The equality constraint is x1 plus x2 equals 1. Typically, the Lagrange function below is used to solve the constrained optimization problem. Lambda is a Lagrange multiplier, and this part is a constraint. The above constraint is expressed like this. Find argmin of this Lagrangian function with respect to x1, x2, and lambda. Differentiate the Lagrange function with respect to x1, x2, and lambda respectively. And find the point where the slope becomes 0. Then you will get the following results. The lambda is -1. In EQP problems, the lambda can be positive or negative. However, for the IQP problem, which we will cover later, the lambda must be greater than or equal to 0. Since the lambda is -1, the x1 and x2 are each 1/2. And the minimum value of this function f is also 1/2. This is the solution to this problem. Let's solve this problem graphically. As seen in the previous video, the objective function is a paraboloid like this, and the constraint is a red straight line passing through 1, 0 and 0, 1. And this gray plane is the feasible region. Then this point becomes the optimal solution. The coordinates of this point are 1/2, 1/2. And the value of the function f at this point is also 1/2. For reference, let's visually check the graph of the Lagrange function L. Let's only observe the x1 lambda and L axes. In this space, the Lagrange function looks like this. It's convex in this direction, but it's concave in this direction. This is the point where the lambda is -1, and the x1 is 1/2. This is a saddle point. This time, let's draw the view from above. This is what you saw in the previous video. If we project the paraboloid onto the x1 and x2 plane, we can draw it as contour lines like this. The further you go in, the lower the contour level becomes. And the constraint is this red straight line. So the optimal solution is located here. The coordinates of the x1 and x2 at this point are 1/2, 1/2. In this way, we solve the EQP problem using Lagrange function. This time, we will solve this problem by converting it to a standard form. This optimization problem can be converted to the standard form of EQP as follows. Since it is an EQP problem, there is only equality constraint in the standard form. And each matrix is defined as follows. Multiplying matrices P and X, we get this. And multiplying this by the transpose matrix of X gives us the function f in the original problem. Multiplying matrices A and X, we get the following results, which is the constraint in the original problem. So this is the same expression as the original optimization problem. The Lagrange function for this standard form is as follows. The first term is the objective function, and the second term is the constraint multiplied by the Lagrange multiplier. Now we differentiate the Lagrange function with respect to x and lambda. The results are as follows. These two equations can be written as a matrix equation as follows. We'll see why later, but first let's find the solution. This part is 2p, and this part is the transpose matrix of A. And this part is matrix A, and this part is matrix X. Here we want to find the x1, x2, and lambda. If we multiply both sides by the inverse of this matrix, we get the following results. Then the x1 and x2 each become 1/2, and the lambda becomes -1. The results are the same as on the previous page. This time, let's look at why these two equations can be written as this matrix equation. The Lagrange function can be expressed as a matrix equation as follows. This equation can be summarized as follows. Here, matrix P is assumed to be a symmetric matrix. Differentiating this equation with respect to x1, x2, and lambda respectively, we get this. Then this part is the matrix 2p, and this part is the transpose matrix of A. And this part is the matrix A. Then we get the following matrix equation. This time, we will solve the IQP problem, which is the inequality-constrained QP problem. Let's solve this problem using the Lagrange method that introduces the slack variable. Let's solve this optimization problem. The objective function is the same as on the previous page, but there's only one inequality constraint. Let's change this inequality constraint to an equality constraint using a slack variable as follows. Since the epsilon squared is always positive or 0, these two expressions are equivalent. This problem then becomes an EQP, so we can solve it as we did on the previous page. The lambda and epsilon can be positive or negative. Differentiating the Lagrange function with respect to x1, x2, lambda, and epsilon, we get the following results. This results in two candidate solutions as follows. Neither candidate violates this condition. However, the lambda value of 0 results in a smaller value of function f. So we choose this as the final solution. An epsilon of 0 means this problem is an EQP. If there is a positive epsilon among the candidates, that candidate is selected as the final solution. Let's check this in the graph method. The area to the left of the red straight line, which is the constraint, is the feasible region. At this point, the function f value in this region is the smallest. So this point is the final solution. This time, we will solve this problem without the slack variable. This problem can be expressed as a Lagrange function as follows. Here, a constraint is added that the lambda is greater than or equal to 0. This constraint is required for the IQP problem. The solutions to this Lagrange function are as follows. Since the lambda is -1, it violates the constraint. In this case, the lambda is set to 0. The negative value of lambda indicates that the constraint does not affect the optimal solution, and lambda should therefore be set to 0. This constraint is called a non-binding or inactive constraint. Let's look at the picture on the right. As on the previous page, this is the feasible region, and the optimal solution is located here. This constraint is inactive. This time we will solve the problem below using a slack variable. This is an optimization problem with an inequality constraint. And the inequality direction is opposite to the problem on the previous page. We will change the inequality constraint to an equality constraint using a slack variable. Then the Lagrange function becomes as follows. Since this is an EQP problem, both lambda and epsilon can have positive or negative values. The solutions to this Lagrange functions are as follows. There are two candidate solutions like this. The first candidate violates this constraint because the epsilon is not real valued. Therefore, we select the second candidate as the final solution. This is the feasible region, and the optimal solution is located here. Therefore, the final solutions to this problem are as follows. Lastly, we will solve this problem without using the slack variable. Flip the inequality direction in the constraint. Then the Lagrange function becomes like this. Since this is an IQP problem, the constraint that the lambda is greater than or equal to 0 is added. The solutions to this Lagrange function are as follows. The lambda is 1, which does not violate the constraint. So the x1 and x2 are each 1/2, which are the final solutions. This is the feasible region, and the optimal solution is located here. The result is the same as using the slack variable on the previous page. So far, we have looked at how to find solutions to EQP and IQP problems using the Lagrange function and slack variables. In the next video, we will solve this problem using the dual Lagrangian method.